Okay, let's talk quite a bit about first-order reactions. So these are reactions that are defined as having a reaction rate double when the concentration of your reactant doubles, or it would triple if the concentration of the reactant were to triple, etc. There's a linear relationship between the concentration of your reactants and the rate of the reaction. So let's say that for a given reaction, A turns into B. In a given moment, half of your A's will spontaneously react into B's. If you were to have twice as many A's, then you would have twice the rate of the reaction, twice as many A's reacting, but still you would only have half of your A's reacting in that given amount of time. You see that the proportion of your reactant particles which react in a given moment of time is unrelated to the concentration of those reactants. Whether you have 2 A's or 4 A's, still only half of your A's will react in a given moment. We see that for first-order reactions, the presence of nearby particles is irrelevant because usually collisions are not required for first-order reactions. Most particularly, this involves decompositions. For example, we have a problem down here in which we have cyclohexane decomposing into, actually cyclopropane decomposing into 1-propene. But also, we can include nuclear reactions, nuclear decompositions. For example, uranium-238 decomposes into thorium-234 and will release a helium-4 isotope, also known as an alpha particle. So you should recognize that nuclear reactions and decompositions are usually first-order reactions. And so we can kind of derive the following equation about first-order reactions, where we have in brackets here concentrations of A at a given time, T, and then also the concentration of A at some initial time, A0, also sometimes known as AI. The natural log of this ratio is equal to negative kT, where K is your rate constant and T is the time that the reaction progresses to go from A0 to AT. Of course, your time needs to be in the same units as the reciprocal time units of your rate constant. Now this reaction, or actually equation, can also provide us with this equation. Ln of A at a given time is equal to negative kT plus the natural log of the concentration of reactant initially at time 0. And now you can see that we've actually seen already that first-order reactions follow this graph, where we can see that the concentration of our reactant decreases over time because we're losing some of it. It's reacting, and so there will be less and less of it as the reaction proceeds. And you can also see that the slope of that reaction decreases. We can see that the rate of the reaction decreases over time. Now, for first-order reactions, we have a changing slope for AT versus time, but we have a line, we have a constant slope for the natural log of the concentration of our reactant versus time. This is because this equation that we saw here, this is actually in a linear form. We see that we can say that the natural log of our concentration of reactant can be represented by y in the linear equation, and then our rate constant can be represented by by m actually, and t is x, so x-axis, and then b is our natural log of a concentration of a reactant at the very beginning of the process. So basically y-axis x-axis, and then m, our slope in the linear form, is equal to negative k. Now, this is kind of important because later on we're going to be able to recognize what type of reactions we have, 0, first, second order, by what type of graph gives us a linear form. And so you should recognize that this is the equation only for first order reactions, and a straight line on the ln of AT versus time graph means that we have a first order reaction. Okay. So kind of using these equations to solve some problems, you're provided with the fact that this cyclopropane decomposes into one propene, and you're told that the rate constant is equal to 6.7 times 10 to the negative 4 reciprocal seconds. This is all that you're told. What is the order of this reaction? Well, one way to know the order of the reaction is to see that it is a decomposition reaction. And decomposition reactions are almost always first order reactions. But another way to know the order of this reaction is by the units in your rate constant. You should memorize and recognize the units of rate constant versus the order of reaction. What are the units for rate constant for all of these different types of orders of rate reaction? Okay, so let's say that you have a zero order reaction. For example, rate is equal to k, where you might have some concentration of a reaction, but it's to the 0 power, so it's really just 1. So that rate is equal to k. What is k? Well, you know, rate is always in this chapter molar per second. So hence k must also be molar per second. What about if you have a first order reaction? The rate law for a first order reaction is rate is equal to k times the concentration of the reactant to the first order, or first power. Now what are the units for k? We'll take rate divided by the concentration of A, rate over the concentration of A. The units of rate are molar per second, and the units for the concentration are in molar. So molar should cancel out, so you're only left with 1 over second. A first order reaction has a rate constant unit of 1 over second. For a second order reaction, there's going to be an additional molar or moles per liter in your denominator, and so that molar up top cancels out 1 molar, and so then you're left with 1 over a molar times seconds. And if you're dealing with a third order reaction, then it's going to be 1 over molar squared per second. Now, you could memorize all of these only by memorizing 1. For example, you can memorize that quite easily. A zero order reaction is rate is equal to k, and so the unit of k is molar per second. And then each time that the order increases, you just divide by molar to get your units. Okay, so what is the order of this reaction then? Our units are 1 over second for the rate constant, hence it must be a first order reaction. Hence, to solve the next several problems, we'll be using the first order equations instead of the 0 or second order equations, which we'll go over soon. And so we say, what is the concentration of cyclopropane that will remain after 4.2 minutes if the initial concentration of cyclopropane is 0.40? So what will be the concentration? What will be the concentration at a given time, AT, given all the other information? And so you're given 4.2 minutes and all these other things, but you can't plug in 4.2 minutes for your time because our k is in 1 over seconds, and so it's important that we're plugging in for seconds here. So the number of seconds that is 4.2 minutes is actually, I don't know, 4.2 times 60. And so this should provide you with ln of AT is equal to negative 1.09. What is AT? Well, you need to get rid of the natural log. And so take the anti-natural log of both sides so that you get e to the negative 1.09. The concentration of A at a given time is equal to 0.34 molar. To get rid of natural log, you need to take the number on the other side as the power of E. That's a big deal, important. Okay, next question. How many minutes would it take from the beginning of that reaction to decrease the concentration from 0.4 to 0.21 molar? So how long would it take? What is the time needed to go from 0.21 molar to 0.40 molar? So plugging in, you should find T, which is going to be 961 watt unit. Your only unit for time is here seconds. So how many minutes is that? Convert into minutes, that's 16 minutes. Next question, how long would it take to react 95% of your compound? You could plug in for 0.40, and then what is the remaining 5% of 0.40? That's 0.2. You could plug in all that, actually 0.02, my bad. You could plug in all that, or you could just plug in any hypothetical ratio of AT versus A0. If 95% of your reactant has reacted, then only 5% remains 100 minus 95. So natural log of 5 over 100, and that solves for 74.5 minutes. Thanks for watching, guys.